Okay. So those of you who are taking it for credit, you have taken QFT1, right? Okay, because this is really going to be sequel to QFT1. So what I'll do is to begin by briefly recalling the results from QFT1 that we are going to use. Okay, not even the results, but the general idea of what we are going to use this course for. So QFT1 essentially you can divide into two parts. Okay, one is the general formalism, okay. And in that context you probably learned that one of the main ingredients of quantum field theory is a Green's function. Okay, Green's functions are important, okay, because given the Green's function, okay, or correlation function, you can extract most of the information about the theory from there. Okay. So for example, if we take a scalar field theory, say with a scalar field phi. Okay, let's suppose we take a single scalar field. Then the Green's function is a time ordered product, vacuum expectational of the time ordered product of operators. So let me explain these various notations. So this is our vacuum. This symbol is time ordered product, okay, which means that whatever be the order of operators inside this product, you always make sure that the earliest time, okay, the one with earliest time in the argument is to the extreme right, the one with the largest time or the latest time is to the extreme left. Okay, that's how you define time ordered product. And this phi hat is a field operator. This is a field operator. Is this notation familiar to everybody?
Sir, is there a e to the power minus, means intracts e to the power minus I t? Intracts?
Well, what I am using Heisenberg picture, right? So these are all operators in the Heisenberg picture. So let me write what phi is. The phi hat of xt is, let me get the signs correct, it's e to the I h hat t, phi hat of x e to the minus I h hat t. So I am using the Heisenberg picture where the vacuum or any state is time independent, okay, and the operators are time dependent. Okay, so this is the Schrodinger picture operator. Okay, this is the Heisenberg picture operator. So I'll be using Heisenberg picture throughout. Okay, in that case you don't have to write any explicit to the IHFT in this. Now, why is the Green's function useful? Okay, for example, you probably have seen that if we know the 2-point Green's function, this contains information about the mass. It's familiar? Okay, you have to take the Fourier transform, write it as a function of p, okay, and then you look for poles as a function of p, okay, where if p square equal to minus m square is the location of the pole, then m is the mass of the particle. On the other hand, if you have an n-point function gx1 to xn, this gives you information about the scattering amplitudes. Via LSZ reduction formula. This is familiar? Okay, so if I give you the Green's function, you can calculate the scattering aperture. So this is a general formalism. Okay. The second aspect of quantum field theory that we have learned is how to actually compute these objects. Right? How do you calculate these 2-point function and n-point function? Okay. And there we use mostly perturbation theory. So we calculate G using perturbation theory. Okay. So what we do is that we write the Hamiltonian H hat as a sum of two terms. One is a free Hamiltonian. Okay, this just represents free fields, which is easy to solve, plus some small parameter which I call lambda times H hat interaction. So this is the free Hamiltonian. This is the interaction term. And this lambda is some small parameter in which you do perturbation expansion. Okay, so we do perturbation expansion in lambda, and this gives rise to what we call Feynman rules. Okay, you get the result as a sum of Feynman diagrams. Okay, and the Feynman rules tell you how to associate with a Feynman diagram an actual expression. Is this okay? Now, one way this course will differ from what we had done earlier is that we will try to use a different procedure for calculating these Green's functions. Okay, we will see that for simple theories like scalar field theory, then eventually it will lead to the same Feynman rules. Okay, nevertheless, the procedure will be different. Okay, and because it's more versatile in some sense. So, the first step will be to use a different approach for okay, and this will be the path integral approach. And as I said, we will see that it leads to the same Feynman rules. For simple theories. Nevertheless, there are several advantages of this approach. okay, using path integral. The first advantage is that it gives a manifestly Lorentz covariant formulation. In the earlier approach, okay, when you do this, for example, okay, defining a Hamiltonian means that you are singling out time coordinate as spatial, right? Because Hamiltonian gives a time evolution, and Hamiltonian by itself is not Lorentz invariant, right? Because it the momentum and energy are treated differently. Of course, the final Feynman rules that you derive for say 5 to the 4th theory, okay, they are Lorentz invariant, right? You can reformulate the result in a Lorentz invariant way, but at the intermediate stage you certainly lose Lorentz invariance because you give time coordinate and spatial treatment. Okay. In contrast, you will see that here throughout we can maintain Lorentz covariance. Okay, that's one advantage. The second advantage is that sometimes the canonical approach or this Hamiltonian approach can become complicated, particularly when the interaction terms have derivatives. Okay, so again I'll try to give an example. So let's suppose that you have a Lagrangian of the form okay, normally you write lambda 5 to the 4, okay, but this is as good an interaction term, right? There's a 4 quartic order in 5. And now suppose you want to treat this in the Hamiltonian formulation. Okay. So let's single out the time part. So this, my notation will be that the eta 0 0 is -1, everything else is +1. Okay, so eta mu nu in my notation, eta mu is a matrix -1 1 1 1. So this gives you half phi dot square minus lambda phi square phi dot square plus space derivative terms, right? Okay, which you don't care about right now. Right? This gives you half phi dot square. Okay, and from here you get minus lambda phi square phi dot square. So from this, if we try to calculate the canonical momenta phi, you have to take the derivative of the Lagrangian functional derivative with respect to phi dot. Okay. So that gives you phi dot from the first term minus 2 lambda phi square phi dot from the second term. So this is phi dot times 1 minus 2 lambda phi square. Okay. So now if you want to derive the new Hamiltonian, well, if you want to derive the Hamiltonian in the presence of this interaction term, Hamiltonian will be integral d cube x phi dot pi minus L, sorry, phi dot pi minus L. Okay. And then you are supposed to re-express this in terms of pi, right? Not phi dot. Hamiltonian is always expressed in terms of pi and phi, right? Not phi dot and phi. Okay. So what will you do? You will have to express phi dot in terms of pi, right? So this gives you phi dot as pi over 1 minus 2 lambda phi square. Right? So this you can easily check, gives you integral d cube x half pi square over 1 minus 2 lambda phi square plus these are space derivative terms. Okay, which is just minus of what appears in Lagrangian. Okay. But you see that here we have something in the denominator. Okay, now of course in quantum field theory, if you have something in the denominator, it's a problematic situation. But in perturbation theory, what we will do is to expand this out in a power series in lambda and derive the Feynman rules from there. Okay. But you see that now we have the problem that it contains arbitrary parts of infinite number of terms. Right? Of course, to a given order in lambda, you only have a finite number of terms. But as you go to higher and higher parts in lambda, you get more and more interaction terms. Right? Because suppose you want to calculate up to lambda to the 10. Then you have to expand this out to order lambda to the 10 and keep all the interaction terms. Okay? So the Feynman rules will become complicated. Is this clear?
How is that different? I mean, once you expand it, you will have one term for one power, right? So you can just take that term.
You can take that term, but when you draw Feynman diagrams, right? Suppose you want to calculate 6-point Feynman diagrams, right? So then you have to include a 6-point vortex.
Yes.
Okay, because this will have a 6-point vortex. You have to include vortices like this. Up to 6 point it may still be manageable, right? But you can already see that the number of terms will keep growing. Number of Feynman diagrams will keep growing because you not only have 6-point vortex, you also have 4-point vortex. But I think this is 2 4-point vortex. Right? In loops, you will get many more terms. Right? So it's possible to do this, but it just makes it more complicated because the number of diagrams increase. Right? If you just naively derive the Feynman rules from there. Right? So it's certainly possible to do this, but it just becomes inconvenient. Okay. We'll see that in the path integral approach, you don't have such problems. Okay, you never get things in the denominator. If the original Lagrangian didn't have things in the denominator, okay, you will not encounter things in the denominator in the path integral approach, in the Feynman rules. But the main reason that you want to do path integral approach is because the path integral approach is much easier to implement for non-abelian gauge theorems. And this will be one of the main topic that will be studied. The non-abelian gauge theories, because this is what is responsible for the strong and weak forces that we see in nature. Are there questions? So I'll give a brief review of path integral approach that we apply in quantum mechanics, but I am assuming that you would have seen it once in quantum mechanics course. Okay, but I'll try to give a review of how it's done. Okay, so path integral in quantum mechanics. Okay, so let's consider a simple quantum mechanical system for which the Hamiltonian has this form. Okay, so the hats basically means that they are operators. This is associated with the classical Hamiltonian. Classical Hamiltonian is E square over 2m plus V of Q, and we can also consider a classical Lagrangian which is half m q dot square minus V of Q. Okay, this Lagrangian gives rise to this Hamiltonian. And you are probably familiar with the action principle, right? If you have a classical Lagrangian like this, then the action principle tells us that you get the equations of motion by extremizing the action. Okay, which is the equation of motion follow from okay, so the action by definition is integral of the Lagrangian. And what one means by extremization is the following, that imagine that we are given some initial time t prime, some initial position q prime, and some final time t double prime, and some final position q double prime. Then you draw some path connecting these 2 points, initial point and the final point. Okay. And then you vary this path till the action is extremized. Okay, which means that the classical path, for classical path, delta S is equal to 0 to first order for any variation of the path. And if you have a class, suppose this was a classical path, okay, then to test if it's classical path, what you do is that you take a neighboring path, calculate the difference in this integral between the neighboring path and the classical path. That difference will always be 0 to first order. Okay? That only then you can say that this is a classical path. Okay, this satisfies classical equations of motion. If this difference is not 0 to first order, then this path is not classical. Okay? That's the action principle. This is familiar? Okay. But of course you want to do quantum mechanics, so let's go back to quantum mechanics. Okay, this is the Hamiltonian. And define certain things and then see how to calculate them. So again, let's go to Heisenberg picture. Okay, so we define q hat of t as e to the power I h hat t. Oh, I should have said I'll set the Planck's constant h bar equal to 1 throughout this analysis, so that you don't have to write this bar 3 times. So this is the Heisenberg picture representation of the position operator q hat. And similarly you can define p hat of t, okay, but I will not write down explicitly. We also define q by definition is the eigenstate of q hat operator. So this I will call q hat. Okay, so if I have not written any argument, okay, that's the q hat of t equal to 0. So I will define this q as the eigenstate of the q hat operator with eigenvalue q. And similarly, I will define, let's call this p prime. These are the prime will mean that these are eigenstates of the momentum operator. Okay. You can consider this inner product q with p prime. Okay, first of all, q with q prime of course will be delta function, right? And p with p prime will be delta function. So p prime with p prime will be delta function. So what about, okay, this object? You know what its expression is? E to the power I qp, right? E to the power I qp. Okay, up to normalization, which we will not worry about right now. And p prime q will be e to the power minus I q. Yeah, that is a conjugate of this one. So we'll also define a state which I will call qt. This by definition will be e to the power I h hat t So what the property that it has is that if you apply q hat of t on qt, okay, if you use this expression, you see that the e to the minus I h hat t cancels that e to the I h hat t, and so this gives you e to the I h hat t q hat on q, but this of course is just q times q, so this is q on q. So this state, which are denoted by qt, is an eigenstate of q hat t with eigenvalue q. Okay, that's one to define this state. Another definition: k q prime p prime q double prime t double prime will define to be the state q double prime p double prime q prime p prime. Okay, we'll take p double prime to be larger than t prime. So this I can write as q double prime
So we are working in the Heisenberg picture.
Yes.
So shouldn't it be that you acting on this q of t on the
Yes.
same q is giving you the same eigenvalue? So why is there a different state at time t? And
Okay.
the state does not
Because if the state was the same, right, then if you start with a state that is an eigenvalue of eigenstate of q hat of 0, right, it will not remain the eigenstate of q hat of t. Because q hat is changing, right?
q hat? Yes.
Q hat is a time dependent operator, right? So if you take a fixed state, right, which was an eigenstate to begin with, it will not remain an eigenstate. Except for Hamiltonian, right? For Hamiltonian, of course, if you start with the eigenstate of the Hamiltonian, it always remains an eigenstate of the Hamiltonian. But Q operator doesn't commute with Hamiltonian, right? So if you start with an eigenstate of certain eigenvalue, right, after some time, it will not remain an eigenstate, right? So on the other hand, by definition, this Qt, right, is a new state which is an eigenstate of Q hat. Right? This is our definition of Qt. Okay? If you don't like this definition, you can just use this as definition, right? We don't really need this definition very much, right? All we need is this aspect of this state. Is this okay? Are there other questions? So what we will do now is to, so of course, if you know the Hamiltonian, we can in principle calculate this. But what we will do now is to give an expression for this that is based on the path integral approach. Okay, we will of course start with this and we will manipulate this to write it in a form, okay, which looks like integration over paths, okay, and then we will generalize this to more complicated objects. So let's define delta as t double prime minus t prime by n, where n is a large integral. Okay, eventually we will take the limit when n goes to infinity. And let's slide that expression okay, n delta is just t double prime minus t prime, so this is an identity. But now I will write this as a product of n factors of this kind. And now I insert a complete set of states here, okay, which will take to the position eigenbasis. So, integral let me call this variable dq n minus 1. This is identity. This is the identity operator by completeness of states, right? This is a complete set of states, so I just integrate over the whole position for it. This is an identity operator. Q n minus 1 is just the name of this variable. Okay. Then here I insert integral dq n minus 2 and so on. So similarly, finally here, but here I don't have to insert anything. Here I insert integral dq1 So this gives you altogether n minus 1 insertions, right, which separates out these n factors. Okay, but we are just inserting identity in each of them.
Sir, when we split these n terms in this e to the power minus I delta,
Yes.
we explicitly assume that there is no time, explicit time dependence.
That's it, yeah. We are assuming that h hat is time independent. Right? If h hat is time dependent, then you have to, instead of using e to the minus I h hat t, right, you have to use time ordered expression. Okay, and then you have to do appropriate time ordering here. Okay, but let's just assume that h hat is time independent. Okay, are there other questions? Okay, if h hat is not time independent, then you couldn't have even written the first expression e to the minus I h hat t double prime minus t prime, because that would have been an time order integral in the exponent, but that has to be time ordered.
Yeah, but that implies this second one is still true, right?
Second one would still be true, yes. Okay, except that each of these will be different h.
Differential.
Exactly. Delta will be still, but these different h hat s will be different. Okay, so what you can think of, what this is doing is that it's taking the state q prime, okay, and instead of evolving it in one stage from t prime to t double prime, okay, this one is evolving it from t prime to t prime plus delta. Okay. Next one is evolving it from t prime plus delta to t prime plus 2 delta, and so on. Okay. And if h is time dependent, okay, then this h hat and the next h hat will be slightly different. Okay. So this expression is still true, right? But you couldn't have written the original expression. That's e to the minus I h hat times t double prime minus t prime. Is this okay? Right? See, writing it this way makes it clear that you are doing an infinitesimal evolution, right? So here you can just take h hat to be its time independent, right? Its central value. Okay, but then different h hats will be different. So this product then I can write as, so this I'll write as product, say I equal to 0 to n minus 1 So with the understanding that Qn is by definition Q double prime and Q0 by definition is Q prime. Okay, then this is like Qn e to the minus I delta h hat Qn minus 1. Right? That's the I equal to n minus 1 term here. Qn e to the minus I delta h hat Q n minus 1. Okay, then the I equal to n minus 2 term and so on. Is this clear? Right? Yes.
Sir, for h being time dependent,
Yes.
We can write the integral as a limit of sum, but then when you are writing this product, the different h, I mean h at different time, do they commit?
No. So that's the point. So the original expression would have been wrong. You shouldn't just write exponential of I integral h dt. That's the wrong expression, right? What you should really do is that you take a time dependent h, then evolve from this state by e to the minus I delta h hat with that corresponding h hat, right? Then you evolve by the deferred h hat, right, to just change. So this expression is still correct. You just shouldn't have written it as e to the minus I integral h of t dt. Okay, that would have been the wrong expression. Okay. Formally you can still write it if you take it as understood that it's always time ordered. Okay. The earliest h's act first, right? Then the later h's and so on. Okay, that's equivalent to this. Okay, but as I said, just to avoid complication, I am taking h hat to be time independent. Okay, so we now want to evaluate this. So, then our goal is to evaluate qi plus 1 to the minus I delta. Now let me write down the expression for h hat. H hat is v of q hat plus p hat square over 2n. Yeah, so the integral I will be performing later. Oh, here. Yeah, yes, thank you. Integral dq2 dq1 to dq n minus 1. Yes. Okay, so you have to evaluate this. So what we'll do is to write this So what have we done? See, so this is like e to the a times e to the b. E to the a times e to the b. Okay, you can combine using the Becker-Campbell-Hausdorff formula. And this is e to the power a plus b. But there are corrections, right? It starts from half a commutator b plus other terms. Now here, because these don't commute, okay, q hat and p hat don't commute. Okay? So clearly there will be corrections. Okay? This times this is not just this. The important point, however, is that the corrections are bilinear in AB, okay, or higher order. Since both of these operators A and B have delta multiplying them, whatever correction term you have here, that's of order delta square. Is this clear? And that's what I have written here. Okay, there are some corrections which is of order delta square, e to the I delta square. Okay. So if we ignore this, we will make an error. Okay, we will make an error whose percentage error is of order delta square. Right? Because when you expand it out, it's like 1 plus delta square times something. Okay, so the percentage error is of order delta square. And now you recall that you have to multiply n such factors. Okay. So even if the error is 1 is small, error in 1 is small, when you multiply by n factors, the error can become large. Okay. And indeed, if the percentage error was of order 1 over delta, okay, then when you multiply n of these, okay, you could get a total accumulation of order 1, right? So 1 plus delta times 1 plus delta multiplied n times, right, can become of order 1. Is that clear? Yeah, because it's like 1 plus n delta, right? N delta becomes of order 1. But if we have error of order delta square, right? If it's like 1 plus delta square, you multiply n times, you will get 1 plus delta square times n. Now delta times n is fixed. Okay. So delta square times n is still delta times t double prime minus t prime. Is this clear? Okay. So if we take the large n limit, okay, then the error that we are making here will not affect the result at the end, right? Because in each step, in each of these terms, you are making an error, which is percentage error is about delta square. Okay. You multiply error of these factors, the percentage error still remains small, right? Because it becomes of order n delta square, right, which is still small. Okay. So for this reason, I can now ignore this term. Okay. But remember that this ignoring this term is valid only in the large n limit. Okay. For any finite n, you are making an error. Okay. But keeping in mind that at the end we will take n to infinity. Okay, we don't worry about this error. Okay, we just drop this term. Okay, and so we have this nice expression over here. Okay, product of two terms. You could have also extended them. Right? You could have brought this first and this next. It will get still the error is of order delta square. Okay, so now this is an eigenstate of q hat. Okay. This is a function of q hat. Right? So what will happen when this acts on this? Okay, this is of course a Hermitian operator, right? So q hat acting on the left and right gives the same thing. So you know the result for this. So what will happen?
Replace q operator with qi plus 1.
We just replace q hat operator by qi plus 1. Right? Any function of q hat acting on the eigenstate q will give you f of q times the same eigenstate. So this then gives e to the power minus I delta v of q I plus 1 Okay. Now we will insert a complete set of states here. But this time it will be the momentum eigenstate. It's clear? So this gives you e to the minus I delta v of q y plus 1 integral dp. Now p hat e to the minus I delta p hat square is acting on a momentum eigenstate. Right? So you can replace p hat by p. Right? Same argument. So e to the power minus I delta p square by 2m. And then you have q I plus 1 p prime, sorry, p, and then p prime q I. This one is e to the power I p qi plus 1, and this one is e to the power minus I p qi. Right, so this becomes e to the power minus I delta g of qi integral dt. Yes.
qi plus 1. qi plus 1. The first factor.
Oh, yeah, thank you. qi plus 1. Okay. So you have to now do this integral. This is a Gaussian integral. Okay, so we'll just complete the square. Let me write this p minus okay, so what I did was that this is a quadratic term and a linear term. Okay, I completed the square over here. Okay, I delta p square by 2m, that's the first term. Then it will be minus I delta, well, yeah, minus I delta times delta by 2m times the cross term. Okay, cross term exactly cancels this and gives you back the p times ip times qi plus 1 minus qi. But then there is an extra term which is the square of this, okay, which I have to subtract out, and that's this term over here. Now this integral, okay, so now you see that this is independent of e. Okay. This integral, I can shift origin, okay, call this p prime, okay, so this becomes something that is independent of q's, okay, just some constant. So I write this as a times e to the power minus iv I delta dqi plus 1 plus im over 2 delta qi plus 1 minus qi square. Is this clear? So now let's go back to our original expression. K q prime t prime q double prime t double prime will be product I equal to 0 n minus 1 of this object. Right? This is what the individual term in the product is what I evaluated. So A times e to the power minus I delta v of q I plus 1 plus I m over 2 delta q I plus 1 minus q I square. So this becomes a to the power n, okay, which will be not too relevant for us, and then exponential. Let me write this. So I'll write as a sum minus I delta. So there are too many i's, but this I is square root of minus 1. Okay, not the, it will be distinguished for the index I. Okay, so let's see what we have done. The first one is straightforward, right? I have just written exponential minus I delta times the sum over this, because the product, right, that becomes sum from I equal to 0 to n minus 1. In the second term, okay, I m over 2, what I have done is that I have taken a delta outside. Okay, so that this becomes delta square, and I wrote that delta in the denominator over here. Okay?
There are integrals over q's.
Yes, integrals over q's. Thank you. dq1 to dqn minus 1. So this is integral dq1 to dqn minus 1. Okay, a to the n, of course, I can bring outside. This is just a constant. Now, what I claim is that this can be written, okay, this can be thought of as integral dq1 to dqn minus 1 of e to the power is. Where s is the action, s is integral L dt, which is integral half n q dot square plus v of q dt. Okay, so I'll now explain how this integral here is related to what we have here. Sorry, there's a minus, right? Lagrangian is the minus right here. Okay. So let's see how, in what sense this is that one. So suppose this is a path. Okay? This is my t prime. This is t double prime. Now let's divide this whole interval into size delta. So this is t prime plus delta. This is t prime plus 2 delta, and so on. Here it will be t prime plus n minus 1 delta. Okay, and finally when we apply n delta, it becomes t double prime. Because t double prime minus t prime is so this is q prime. So let's call this q1. I'm just renaming it. Okay, call this q1. this as q2 and so on. Okay, take a path, arbitrary path. So forget about this expression over here altogether. Okay, I'll try to make connection with this one later. Okay, but right now, let's see how we can represent the action. So take an arbitrary path like this. Divide this time interval into intervals of size delta. Okay, and for every delta, whatever the value of q you have for that path, you call this q1, q2, etc. Okay. In that case, integral v of q dt, the minus sign, minus integral v of q dt. Using the definition of integral, I can write this as minus delta Is this clear? Right? This is the definition of an integral, right? As a limit of a sum. Okay? I take the sum of these intervals and I multiply by delta, okay, just to compensate. I mean, otherwise you write it as t prime t double prime minus t prime over delta, okay, times this sum. Is this point clear? Clear. See, v was 1. Let's just check the normalization. If v was 1, then this will give you n times delta, right? Which is t double prime minus t prime. If v is 1, this side will give you t double prime minus t prime. That is still n times delta. Okay, so that fixes the normalization. Now, t dot prime minus t double prime half m q dot square dt. Okay, so now let's try to calculate this. Okay. So this is, again, write it as a sum. So delta, first half m times delta, sum I equal to 0 to n minus 1, q dot at t prime plus I delta square. I have to calculate q dot. Okay, what is q dot? Q dot is the slope. Then for this path, q dot you calculate by calculating the slope. Okay. But you have to calculate the slope in this ith term, t prime plus I times delta. Okay. That's the particular time interval for time at which you have to calculate the slope. This is our t. Right? T, the running variable, is t prime plus I delta. As you are summing over I, you are integrating over t. But this one, I can write as q I plus 1 minus qi over delta. Yeah, delta is the interval. Okay. So you calculate the I plus 1 value minus ith value divided by delta. So that's this one. So now you are more or less done. Just have to put things together. So e to the is is e to the I. First you have this one, so it's minus I delta, plus I by 2 and this is exactly what we have here. Yeah, so it is in this sense that you can think of this as exponential of I times s. Is this clear? So formally one writes this as k q t q prime t prime q double prime d double prime as integral dq e to the is. Well, there is a normalization. Let me put some arbitrary normalization. Okay, it will not really matter at the end. So this is some normalization. So what does this symbol mean? Okay, this formally is the sum of our paths, okay, or integral of our paths. Okay. But in practice, what it means is the following: that when you have an expression like this, okay, this is sum of our paths. So this I should write that, of course, when you write dq, okay, I should tell you which paths you should integrate over. Okay. The path should start at q prime t prime and end at q double prime t double prime. Okay. So you fix the endpoints, okay, and integrate over all paths. Okay, that's what this is formally saying. Okay. And for any given path, the weight factor is e to the is. Okay. But in practice, okay, when you actually try to implement it, what you will do, of course, you cannot integrate over continuous paths. Right? You will break the path into many segments. Right? Just like what you have done here. A path is a collection of q values at regular intervals. Okay. You break the path into many segments, then you represent the action, okay, which was an integral to begin with, okay, as a sum, okay, which is a function of the q values at those segments. Right? Once you discretize the action, right, it depends only on the q values at these points. Right? As you can see here. Right? This depends only on the q values at those particular intervals. And then what you say when you say we integrate over path, right? What you mean precisely is that you integrate over each of those qi's. Because that is like integrating over path, right? As you vary a path, okay, what will happen? Each of these qi's will change. Okay? So the definition of what you mean by integrating over path, okay, is simply that you break up the path into segments and then you integrate over the q values for each of those segments, okay, for each point. So it becomes a regular discrete integral over a discrete set of variables, okay, as opposed to a continuous set of variables, right? Because you don't know a priori what you mean by integrating over a continuous set of variables. Okay, so you break it up into discrete set and you integrate over each of them. Is this point clear? Okay. So when I write something like this, this is what will mean, right? That you discretize and then you integrate over each of those variables, discrete set of variables. Okay, are there questions? This is. Yeah, explain the
differential dq.
Yeah, so this basically means, okay, this. It basically means, well, I have this. It basically means this. Right? The integrate over q1, q2 up to qn minus 1. Okay, so you take a given path, okay, you take q prime t prime, the initial point, final point, those are fixed. Okay. Now consider, divide the integral into several intervals, right, n intervals, and then you say that for t prime plus I delta, okay, at this time q takes some value, let's call this qi. Okay. Of course, if you have fixed a path, you know what qi is, right? But you have not fixed a path. You are supposed to integrate over paths, right? Okay. So then qi's are not determined. It's these qi's that you integrate over. Right? So specifying a path in this case will mean specifying the qi's. Once you have specified the qi's, right, then you can evaluate the action by this formula, right, discretization formula. That is your weight factor. And then integrating over paths in this language means integrating over each of the qi's. Right? You can say that as you are integrating over the qi's, right, the path is changing. Right? Different configuration of qi's correspond to different paths. Right? So what we mean by integrating over paths is integrating over the qi's. Is this point clear? Okay, so this dq is by definition this.
And sir, every q will be varied from minus infinity to infinity.
Yes, every q will be varied from minus infinity to infinity, which means you are actually summing over paths which fluctuate widely. Right? I mean, this one, for example, can be here, this one can be there. Of course, it may happen that the integral receives contribution only from smooth paths. Right? That may happen. It may not happen. It depends on the details of the form of the action.
But sir,
Yes.
if we take within time delta, if I take 1 point here and 1 point here,
Yes.
so within this time delta, we are considering suppose the paths which are actually not causally related. That can happen, right?
That can happen, yes. And you are
So-
supposed to integrate over all of those.
So, so this all over path integration is not means. So that also we are taking that causally those 2 points are not related within this small time. The information cannot get.
Yes, so now you are not imposing, for example, that this qi plus 1 minus qi over delta, which is the velocity,
Yeah.
is less than c.
Yeah. That
Eh?
cannot impose it.
Yes, that's true. You are not imposing that, but eventually you have to make sure that your final theory is causal.
Yeah.
And it doesn't allow things to propagate faster than light. Yeah, but at least at the level of the path integral, you don't put any restriction that you only sum over causal paths. Right? It could happen that the particle at time t is at one point, and the particle at time t plus 1, okay, at a completely different point, which would be possible if the particle had moved at a velocity a lot faster than c. Okay, so at least at the level of the path integrals, you don't impose any constraint that the paths have to be causal. Is this point clear? Any other questions?
Sir, how can we fix the normalization constant?
Well, as you will see, the normalization constant will not be needed, right? Because finally the quantity that we'll be interested in is this Green's function, right? Which is a ratio of two quantities. Right? You had the time order product in the numerator and also the normalization of the vacuum in the denominator. And when you calculate the ratio, this normalization constant will disappear. Yeah, that's why you don't really have to worry about the normalization constant. Any other question?
At any finite n, we still have that 1 over n correction that we
Yes.
dropped
So at
off.
any finite n, of course, you will always make an error,
Yes.
right? And the hope is that the error will go to 0 in the limit when n goes to infinity.
And that integral will also not do anything to it.
Yes, you have to make sure that the integral doesn't do anything to it. Yeah. Okay. I mean, you don't know a priori that this will give a finite result as n goes to infinity. Right? It's a formal object that we have defined. Right? For quantum mechanics, at least one can show explicitly that this does give finite result. Okay, for physical quantities. Okay, now let's consider a somewhat more general quantity.
So also we can fix the normalization by saying that k q prime t prime to that quantity
Yes.
gives that physical meaning that the particle starts from t prime at time t prime and goes to q dot prime at time t dot
Double
prime.
prime, yes.
So if we can integrate over q dot prime, then it will give 1 because
Total probability amplitude, yes. You can fix it that way also. Yes. Okay, but in quantum field theory, as you will see, there will be things are much more complicated. So, I mean, this works in quantum mechanics, but in quantum field theory, it's hard to fix the normalization constant that way. Right? But we will not really need to fix it, fix the normalization constant. Okay. So here we have a time ordered product, and we will assume that T double prime is larger than T1, T2 up to Tn, and this is larger than T prime. Okay. But these themselves can have arbitrary ordering. Okay. Time ordering means that you always have to make sure that the earliest one comes to the right, okay, the latest one comes to the left. Okay. But T prime is always earlier than everything else. Okay, and this is later than everything else. Okay. So let's suppose that the correct ordering is T tilde n greater than T tilde n minus 1 T tilde 1, where this set T tilde 1 to T tilde n, this is just rearrangement of T1 to Tn. Okay, T1 to Tn may not have any ordering, but we just re-level these variables by T tilde 1 to T tilde n so that they have the correct ordering. Okay? Okay. So then this is given by Q double prime T double prime. Now I will not write time ordering anymore. Q hat T tilde n, Q hat T tilde n minus 1. So I can write down in the Hamiltonian formulation. I just rewrote everything in the in terms of the this Q hat part, that Q hat T equal to 0. So this is similar to what we had done earlier, except that some Q hats are sprinkled throughout. Okay? Otherwise, it's the same integral that the same expression that we had earlier. And our goal will be to figure out what the effect of these q hats are. Right? We want to write a path integral expression for this, taking into account the effect of these q hats. Is this okay? So let's suppose that t tilde 1, let's call this t tilde I minus t prime as ki delta. Okay, so ki is by definition t tilde I minus t prime by delta with some I'll assume that ki's are all integers. Okay, see, by taking delta to be sufficiently small, you can always make sure that t tilde I minus t prime is an integral multiple of delta. Okay, and let's assume that we have done that, so all the ki's are integers. So now let's see what is going to happen. So we proceed as before. So this one is e to the minus I h hat times delta e to the minus I h hat delta this will be k1 times. Right? Because t tilde 1 minus t prime is k1 times delta. Okay, so there will be k1 times this operation. This all, of course, they are even earlier. Okay? There are n altogether factors e to the minus I h hat delta, so k1 are certainly there. And we proceed as before by applying here we insert q1, then you insert q2 integrate over this, and then finally here you will insert q1, qk1. So you see, one factor is followed by q1, two factors is followed by q2, so k factors will be followed by qk, k1 factors will be followed by qk1. Is correct?
What is the relation between I and ki?
I and ki, okay, t tilde I, this I is the I takes value 1 to n, right? Those are the places where you have inserted. So ki is t tilde I minus t prime by delta. That's the definition of ki. So k1 is t1 tilde minus t prime by delta. K2 will be t2 tilde minus t prime by delta, and so on. That's the definition of the ki's. Is that clear? Right? So q hat t, I mean, you can see that why is this important? That it's important because between the first q hat and this q prime, there are e to the minus I h hat t1 tilde minus t prime factor, right? This is k1 factors of e to the minus I h hat delta from this definition, right? t1 tilde minus t prime is k1 delta, right? So e to the minus I h hat delta applied k1 times will give you e to the minus I h hat times t1 tilde minus t prime. Right? That's the significance of this factor. So k1 factors have come, but then something new happens. We have a q hat inserted. Yeah? Okay? Then it's the usual stuff. E to the minus I h hat delta. Now there will be k2 minus k1 times. This will come. Here you will get qk2, and then another factor of q hat inserted. Is this clear? You see here, between these, there are q1 factors of e to the minus I h hat delta, right? Then a q hat insert gets inserted. Then e to the minus I h hat delta k2 minus q1 factors, right? Then again another insertion of q hat here, and so on. Okay? But now you see that because q hat acts on a q eigenstate, right? This just gives a factor of qk1. Right? Here q hat acts on q eigenstate, this gives a factor of qk2. And so on. Is this clear? Then what's the result of path integral? Okay, then you just calculate, carry out the analysis exactly as before. So this then can be written as integral dq. Okay, let me write dq2 to dq n minus 1 e to the is. Okay, this is to be discretized. And then there is a factor of qkn minus 1 up to qk1.
So those integral will now be dq k2 qk.
No, the integrals are over all q's, which includes in particular dq k2, dq kr and so on. Right? But these integrals also you have to do, right? The q1, q2, these integrals also you have to do. Right? The only additional thing are these factors.
Yeah.
dq1 to
dq, yes, dq1, thank you. It starts from dq1 to dq n minus 1. Is this clear? But what is qk1? Right? If you go look at this picture again, what is qk? Right? Qk means that you have gone k delta from t prime, and the value of q that you get here is qk, right? But t prime plus k delta is our t tilde k, right? So this then I can write as q of t tilde n, q of t tilde n minus 1 up to q of t tilde 1. Right? That's the interpretation in terms of the paths. Right? As variables of integration, q1, q2 up to qn minus 1, you had the qk1, qk2 up to qkn. But when you think of what it means in terms of paths, right, for a given path, qk is just what you get the value of q at t prime plus k delta. Is this point clear? But now you say this is an ordinary integral, right? These are not operators. This is just an ordinary integral you are doing. Okay? So how you order this has no relevance. Right? You can order them in any way. It's an integral is an integral, right? We also know that the set t1 tilde, t2 tilde up to tn tilde is the same as the set t1, t2 up to tn, just rearranged. Okay? So I can write this as integral dq e to the is q of t1 to q of tn. Is this clear? Now, if you think of this in reverse, right? what it is saying is that if we calculate anything like this, doesn't matter how the TIs are ordered, what it calculates is a matrix element of the time ordered product. Okay? So path integral automatically computes the matrix element of path integral of time ordered product. Right? You don't have to say anything about time ordering here. Okay? In fact, if you didn't have time ordering, if you want to calculate matrix element of something which is not time ordered, then there is no direct path integral expression for this. Well, you can write it down, but it's much more complicated. Okay? The standard path integral expression that we write always gives the matrix element of time ordered product. Is this part clear? Okay, so our next task will be to extract from here what you want, namely the vacuum expectation value of these. That's what we really want, right? We don't want to calculate between q prime t prime and q double prime t double prime. We want to calculate the vacuum expectation value. In general, the vacuum is not known in terms of q. Right? The vacuum may be the wave function of the vacuum, may be a complicated object, right? We don't know what it is. But nevertheless, we will see that without knowing what the vacuum wave function is, it is possible to extract from this the vacuum expectation value. Okay, so maybe I'll do that next time. Okay, and then we will generalize it to quantum field theories. Okay, once we learn how to do extract vacuum expectation value of time ordered products from path integral.
So here C1 to Tn are arbitrary.
Yes.
So can you please emphasize how is the same delta will be able to get integer number of intervals?
Well, the point is, eventually we will take delta equal to 0, right? So you can always choose t's to be integral multiple of delta, right? Because the error that you will be making is a order delta, right? See, as long as the function that you are looking for is a continuous function of the ti's, right? If you just adjust them a little to make sure that it's an integral multiple of delta, right? You are allowed to do that. Okay? So that's, we will assume that you have always chosen your t's to be integral multiples of delta. Right? And as I said, as you take delta to be smaller and smaller, okay, you can always do this is with arbitrary small error. Essentially, the lattice becomes fine, right? As you take delta to 0. Right? The interval, I mean, you are breaking up the interval into lattice points, right? But the lattice size, delta is going to 0. That means lattice is becoming finer and finer. Right? So, given any arbitrary point on that real t axis, okay, there is always a lattice point arbitrarily close to it. Right? And the delta goes to 0 limit. So, you just pick that lattice point. Is that clear? Yes.
This top right two questions, how did you go from the top one to the next one?
How did you go from this one to this one? Oh, I just wrote each qt. I used the fact that q hat t is e to the I h hat t q hat e to the minus I h hat t. Okay, once you use this and this one, there are two things which are used. One is this one. The other one is that this q prime t prime is e to the I h hat t prime times q prime, and q double prime is q double prime e to the minus I h hat t double prime. Okay, so once you substitute this here, right, you get to this, right? Because this gives you, for example, e to the minus I h hat t double prime. Right? This has e to the I h hat t tilde n to the right, to the left. Right? Those combine to give you e to the minus I h hat t double prime minus t tilde n. So it's exactly the same kind of analysis that we were doing earlier. Is this point clear? Maybe I should have done this a little carefully. So we are simply representing each of these are Heisenberg picture operators, right, by the fact that you can rewrite this as e to the I h hat t q hat e to the minus I h hat t. Okay, that's what brought you from here to there. Is this clear or not so clear? Right, okay, maybe I can do You start from here. Okay. So you get q double prime e to the minus I h hat t double prime, right? That's the q prime, t double prime, t double prime. Then q hat t tilde n gives you e to the I h hat t tilde n q hat e to the minus I h hat t tilde n. The next one, q hat t tilde n minus 1 e to the I h hat t tilde n minus 1 q hat e to the minus I h hat t tilde n minus 1. Right? So now you see that these two combine e to the minus I h hat t double prime minus t tilde n. These two combine e to the minus I h hat t tilde n minus t tilde n minus 1 and so on. Right? So you may see similar, that's what we have here.
We are involving both state and the operators.
No, we are using Heisenberg picture, right? So you are not evolving the states. Okay? States are being evolved just because it's the definition of qt are given. Right? The definition of q prime t prime. Right? Don't think of this as the evolved state. Right? Q prime t prime is just a state which is an eigenstate of q hat of t. Right? And that's what determined the form of q prime t prime as this. E to the I h hat t prime times q prime. Right? So this is not the evolution in the Schrodinger sense. Right? This in fact doesn't satisfy Schrodinger equation. Right? That would have been a minus I h hat t prime. Okay, this is by definition the state, okay, which is an eigenstate of q hat of t prime. That which you can easily verify, right? This is an eigenstate of q hat of t prime. Okay, because this e to the minus I h hat t prime will cancel this e to the eigenstate h hat t prime. So the whole thing is being carried out in the, as far as the quantum side is concerned, right? Everything is being done in the Heisenberg picture. Okay. But of course the path integral doesn't care about any operators, right? Path integral is just a classical integral.
Our operator, position operator, which is evolving in time. So if we take its expectation value in these states
Yes.
that are evolving in time,
Yes.
we will get the same value.
Exactly. That's the definition of this state. Okay, in fact you don't even have to take the expectation value, just calculate the eigenvalue. Right? This is supposed to be an eigenvalue, eigenstate of the position operator at time t prime. Okay, which is different from the evolution of the state using the Schrodinger picture. Yes.
So you mentioned something about path integral expression for out of time order coordinators. Could you elaborate on that?
Well, no, I'll not elaborate on that at least. Certainly not now. I mean, it's a much more complicated expression. Right? You have to use complex integration contours and so on. So, the standard path integral will generate time ordered expression. Any other questions? Okay, so tomorrow we meet at 2.